All right, we're going to continue on the example from last time. So last time we found R1 is half, R2 is -1. Now we're going to plug in the Frobenius series to try to determine the coefficient Cn. So the Frobenius solution is in this form. And here we did not specify what R is because we know both R1 and R2 will give us a solution according to Frobenius theorem. So we're going to just keep the notation as R until we have to plug in the numbers. So then we distribute x to the R inside, and then we calculate y prime and y double prime. And then we're going to substitute that into our original differential equation without the fractions. So we have 2x squared times y double prime plus 3x times y prime minus x squared plus 1 times y must equal to 0. So next, we are going to distribute those terms inside the sigma notation. So distribute them in. And here there's a minus in front, so make sure we distribute the minus to both of them. And then we are going to write everything in terms of x to the power n plus r. So that means we have to rewrite the third term. Rewrite it and then change the starting value of the index. Okay. So next, we are going to write out the terms corresponding to n equals 0 and n equals 1. Sorry, this is a 2. And then corresponding to n equals 1. Same thing here. Oh, I have a, sorry, this should be, the 3 is already inside, so. Oh, I forgot the infinite term here. This is n from 2 to infinity. Here, sorry about that. And then we have the summation. And then we do not have to change this index, but we have to change the last one. All right. Now we're going to combine like terms. This is all the x to the power r terms. These are all x to the r plus 1. And then combine the summations. And then we're going to set them the coefficients equal to 0. And factor out the C naught. And notice if we divide both sides by 2, over here is exactly the equation that we had in terms of R1 and R2. So if C1, C naught is not 0, then this equation has to be 0. That means R should be half, or R is -1. Now, the coefficient for x to the r plus 1, we set them equal to 0. And then we can factor out the C1. And simplify. This tells us C1 has to be 0, or this quadratic has to be 0. But we know the R1 and R2 we got, these are not the roots. So this quadratic cannot equal to 0, because the R value we're going to plug in is either 1/2 or -1. And they won't make this equation be 0, so that implies C1 has to be 0. Okay, now we look at the coefficient of x to the n plus r, set it equal to 0. And we can put all the Cn terms together. And then we can divide to solve for Cn. And then simplify the denominator. We derive the recurrence relation. This is true for n greater than or equal to 2. So now we're going to consider each option for r. If r equals half, so this is our first case. Then Cn is, by the recurrence relation, and then simplify. Here, I'm not going to go through the details of simplifying the denominator, but you can check. It's going to be simplified to be 2n squared plus 3n. And then we can write out the first several terms when n equals 2. equals 3, n equals 4, n equals 5, n equals 6, so y1x is plugging in what CNs are, and they all depend on C0, so we can factor that out. And R1 equals half, so there's an x to the half there. And since we don't know what the closed form expression is, so we're going to leave our answer like that. And then for the case when R2 equals -1, using the same recursive relation, but with R replaced by -1, simplify, then plugging in C2 is C3 is again 0, C4, C5 is 0. So all the odd index is going to become 0. So then our y2x is with r equal to -1 and factor out a C0. So this is our solution. Let's look at another example. So this one is very similar example as the one before. I would like you to use this as an exercise. Problems in this section are usually quite long. So to solve this problem, give yourself enough time. I would say probably at least 30 to 40 minutes to solve it. And then in class, on Wednesday, we're going to either Tuesday or Wednesday, depending on where people are, we can go over this together. I will also have the notes out for this so that you can compare your solution. All right, so that will be all for this section.